Look at this. Put the document with the answer first, and the model gets it right. Move the same document into the middle without changing a word, and accuracy falls from 75.8% to 53.8%. The text still fits. The evidence is still there. So the problem is not what entered the context. It is what actually influenced the answer. How does that happen? Let's start before transformers were a thing. One common design was the recurrent neural network, or RNN. It read text one word at a time, carrying a small running memory as it went. Every new word changed that memory. But RNNs had two major limitations. First, RNNs struggled with long-term dependencies. That simply means connections between words that are far apart. Second, training could become unstable. The gradients used for learning could fade away or grow too large. These are called vanishing and exploding gradients. Either way, learning from distant words became difficult. LSTMs improved this with gates that help the network keep useful information for longer. But the model still had to read the text one word at a time. Transformers took a different approach. Instead of carrying one running memory through the sentence, they could look back at earlier words directly. A word near the end could connect to one near the beginning. This helped with long-range connections. It also allowed many words to be processed in parallel during training. You might think that solved the problem. Earlier words were still available, so the model could simply look back. That would be convenient. In practice, the model still has to find the useful words and ignore everything else. With one short document, that may be easy. Now add more documents with similar names, dates, and details. The correct sentence is still there, but it has more competition. When a model gets worse at using information as the prompt grows, people often call it context rot. The name is dramatic. The words are not literally decaying. It describes the failure we can observe, not one single cause. The lost in the middle experiment gives us a clear example. Put it at the end, and it recovered to 63.2%. Those prompts averaged about 3,000 tokens and never exceeded 4,000. This was not a case of overflowing the context window. In the worst position, the model did slightly worse than its closed-book score, answering without those documents at all. That does not mean every model always forgets the middle. Some models and tasks show a weaker effect. The experiment shows that a model can accept a passage without using it reliably. Many needle-in-a-haystack tests give the model strong word matches between the question and the hidden information. That can make the task closer to searching than understanding. The no-lemma benchmark removed most of those matching words. The model had to recognize a relationship before it could find the evidence. At 32,000 tokens, 11 of the 13 tested models fell below half of their own short context performance. And sometimes, the extra text does not need to be long. It just needs to be tempting. In another experiment, researchers used grade school maths problems. The original problem stayed intact, but they added an irrelevant sentence, often with another number that sounded as though it might matter. Accuracy dropped, and models sometimes used the irrelevant number in their calculation. So the model has to find the right evidence without being pulled towards the wrong one. Attention is involved, but the common explanation is too tidy. A model does not have one fixed cup of attention that gets watered down evenly as tokens arrive. Transformers use many attention heads across many layers, mixed with information carried through residual pathways. A long prompt can fail during retrieval, during the combination of evidence, or later while the answer is being generated. Researchers have found positional biases in some models. Passages at the beginning and end can receive more attention, even when their content does not deserve it. Correcting part of that bias improved middle position question answering in controlled tests. That makes position one contributor, not the complete cause of context rot. For the opening example, we cannot point to one faulty attention head. We can still test which information controls the answer. When the decisive sentence appears on its own, it has a strong influence. Add similar dates, names, and instructions, and that influence can weaken. The model may follow a distractor instead, or it may fall back towards a familiar answer learned during training. Both answers come out through the same language generator. The supported answer does not have a special, honest voice, and the unsupported answer does not arrive twirling a moustache. They can sound equally polished. People sometimes use context rot and hallucination almost interchangeably, but it is useful to separate them. Here, I'm using context rot to mean that the model gets worse at using the material in its prompt as that context becomes more difficult. Hallucination is the false or unsupported output that can result. Poor use of context can end in a false answer, but it can also end in a refusal, a vague answer, or a request for clarification. In those cases, the context has failed to help, but the model has not necessarily hallucinated. The reverse is also true. A model can hallucinate from a short prompt. The relevant fact may be rare or missing from its training, its learned information may be wrong, or its reasoning may simply fail. None of that requires a long context window. So why are models often pushed towards answering instead of saying, "I don't know"? One reason is the way we train and evaluate them. Many benchmarks award a point for the correct answer and 0 for a wrong one. But "I don't know" often gets 0 as well. If guessing has some chance of being right while abstaining has none, accuracy-based scoring rewards the guess. Apparently, confidently trying your luck is sometimes the better test-taking strategy. That incentive does not explain every hallucination. But across training, evaluation, and model selection, it can reward systems that guess rather than abstain when uncertain. In the opening test, the chain might look like this. The correct sentence enters the context window. Its position and the surrounding material weaken its influence. A distractor or a familiar pattern pulls harder. The model keeps generating, and the wrong answer comes out sounding perfectly normal. The text was still there. It just did not control the answer. You can test whether that happened. First, remove the irrelevant material and ask again. Then move the decisive passage to the beginning or end. Give the model that passage on its own. Finally, ask it to quote the exact sentence supporting its answer. If it succeeds with the passage alone, but fails when the surrounding material returns, you have evidence of a context use problem. If it fails even with the passage alone, then we haven't shown context rot. Something else is going wrong. Return to the opening. The answer never left the document. What changed was the route between that sentence and the model's reply. RNNs struggled to carry early information through a long sequence. Transformers gave later tokens a more direct route back. The model still has to choose which part of the prompt should control the answer. So when a model invents something despite having the correct document, don't ask only whether the answer fitted inside the window. Ask which evidence actually won.